Okay. This was in no way supposed to like stress you out, okay? I wasn't trying to give this to you to like see if I could catch you unprepared. I really thought last class that this would be a nice, easy 100 for you, since nobody seemed to have any issues when I was discussing it. Was that incorrect?
Kind of bias in like the last few minutes.
The last few minutes?
Just to help those out that weren't paying attention those last few minutes.
Nobody doesn't pay attention the last few minutes. Everybody pays attention the whole time.
Let's see if we got them right.
Okay, so let's see. What you need to do is come up with some sort of representation for both of these angles, all of them, right? Positive and negative, every possible.
Pi over 4 plus n pi.
So you start with this angle, pi over 4. That's going to be part of your answer. And you notice that this angle is directly across from it. So just add a pi to get over here. And then add another pi to get back, another pi. So really, this is kind of your starting point. You start at pi over 4. And then to that, you just add any multiple of pi, so plus n pi. That's it. Now, I never showed you degrees, how to do this in degrees, but just in case somebody did, this would also be acceptable. 45 degrees plus n times 180 would be okay. Although I don't use this notation, you probably won't ever see this in the book. All right, number 2, you got 4 of them, right? So you could start at 0 and then just rotate by pi over 2, and then another pi over 2, and another pi over 2, and another pi over 2, and then you just walk your way around.
You could start from like any 0.
You could start at any of those, though. Okay? Now, so I could start at 0 and then add to it n times pi over 2. And then I don't even need the 0, do I? I could just put n times pi over 2. Did someone start from somewhere else?
Yeah, pi over 2.
Yeah, so that would have been perfectly fine to do this. That would have also been the same correct answer. It's an infinite list of numbers, so that would be all right. This one, the problem here is that you can't jump around. You can't like rotate out to this one and then just jump to this one and jump back, because every time you jump, it's a different size angle. With all of these, it was the same size each step, right? Each time around. So here, there's 2 different sets of answers. One of them is, first of all, what's this angle?
Pi over
7 pi over 6. And then you have, the only way to get that answer again is to go all the way back around to it. So n times 2 pi. And then you need this angle, which is 11 pi over 6. And then plus n times 2 pi.
Would you accept as negative pi over 6?
Yes, I would have, yeah, because all it has to be is, your starting point just has to be a valid coterminal angle. It doesn't have to be the one I'm using. Yeah? Okay. All right. Okay, so I hope that, anyone have questions over that? Yes? Go ahead.
I put 7 pi over 6 plus 11 pi over 6, and then 11 pi over 6 plus like whatever this is.
Where, here? On this
Like,
one?
I put 7 pi over 6
Plus.
11 pi over
She tried to put it all in one.
You tried to make it all one? Did you try and give like one answer for it?
I gave 2 answers, but I gave like answer from like this and then like that. Can you do it like that?
Like this and then like that?
No.
Let me look at it. I'll look at it and I'll see, and I'll let you know. Okay. All right. Let's finish up what we didn't have a chance to finish last class, which was the graphing of cotangent. So cotangent x, f of x equals cotangent x. So what does this look like? Well, we know that cotangent by definition is cosine of x over sine of x, right? That's the definition of cotangent. It's the reciprocal of tangent. All right? So automatically from here, we know we're going to have problems where?
0.
whenever sine is 0, right? Whenever sine is 0, we're going to have issues. So I already know when I go to graph this that anywhere that sine is 0, I have problems. And if we just recall, sine starts here, goes up, and then down like that, right? So I know that I'm going to, well, you know what? I'm going to do my sine curve over here. Let me do sine x, and then I'm going to actually graph cosine also. So cosine looks like this. So anywhere that sine is 0, cotangent's undefined, right? Undefined. So that means at 0, I should have that vertical asymptote. And at pi, I should have vertical asymptote. And at 2 pi, a vertical asymptote. In fact, at any multiple of pi, right? Even if I kept going out, 3 pi, or if I went negative pi, negative 2 pi, I would have these vertical asymptotes. All right, can you tell me, is there anywhere where the cotangent function would be 0? When the cosine is 0, right? And cosine is 0 at pi over 2 and 3 pi over 2. So pi over 2, isn't that right here, halfway? So right here, and then I have another x-intercept right here. You all with me? What do you think the behavior of the cotangent function will be as I try and draw it towards these verticals? What do you think it's going to do? It's going to do what tangent did, like take off, right? Like get real big, or it's going to be asymptotic. So let's try and figure out what that sort of behavior is going to be. So let me try and pick an angle. This was pi over 2. Let me try and pick an angle over here like pi over 4, which would be halfway. And if we try pi over 4 into this, we all know that cosine of pi over 4 is root 2 over 2. And we know that sine of pi over 4 is also root 2 over 2. So the ratio should be 1. So I know that at pi over 4, I'm at 1. And then what about as we start to plug in numbers that are smaller and smaller and smaller?
It's going to rise.
It's going to rise. And the reason it rises is because what you're doing is you're getting smaller and smaller angles, and you're taking this red curve and dividing it by the black curve. So the red curve is big, right? The black curve is small. Big number divided by small number, big number. So it starts to become large and takes off like this. Now, what happens when I'm on the other side over here, like at 3 pi over 4? 3 pi over 4 is before pi, right? 3/4. I'm going to have negative 1 there. Because if you go to 3 pi over 4, you're in the second quadrant. The x and y coordinates are the same, but they differ by a sign. So you're going to have negative 1 there. And then for the same reason, as you move towards pi, the ratio, so here's pi here. So the ratio is you have a small sine value, and you have a large negative cosine value. So if you have a big negative number over a small positive number, you should get a large negative number. And what do you think it does in that second pair of vertical dotted lines? Just the same thing, right? So it's going to go like this. It kind of looks like tangent. If you go back and look at tangent from last class, it looks very similar. I'd like to graph tangent and cotangent together on the same axis, just so you can see the difference between the two. So I'm going to do a new graph here. And do you remember where tangent had its issues? Where it had its verticals? It was at pi over 2 and over there, but I told you that the standard place we like to look at it is between negative pi over 2 and pi over 2. That's like the standard period that we like to look at with tangent. It was like this. You can just look in your notes from last class. x-intercept here. This was tangent of x. So what was the period of tangent? What was its period? Pi. That's how long it took for it to repeat itself. So from negative pi over 2 to pi over 2, the period was pi. Over here with cotangent, what's the period? Pi. All right? So our periods are the same, but where they start and end are different, right? Here the period is 0 to pi, then pi to 2 pi. Here it's different. It's negative pi over 2 to pi over 2, then pi over 2 to 3 pi over 2, right? And you could keep going with that. So same length period, but the starting and end of those periods are different. Yes? All right. Also, the tangent function is what we would call an increasing function on this period, meaning that if you read this like a book from left to right, you're going to be going up, aren't you? So it's increasing within this period. Whereas the cotangent function, within its period here, if you read it from left to right, you're going down. So this is a decreasing function. They both have a single x-intercept in between those verticals, right? What about range? Range is everything for both of these, right? Both tangent and cotangent have an infinite range. Domain is going to be a little different, though, right? The domain is, we would say it's, well, how would we say this? How would we say the domain of this?
Negative pi over 2.
It can't be pi over 2. And it can't be this, right? So we would say x cannot be pi over 2 plus n pi, right? That's how we'd say that?
Yep.
Okay. And then over here for this one, we would say, where do we have our problems? At 0 and pi, right? So at pi, 2 pi, 3 pi, 4 pi. So we would just say x can't be n pi. So this is your domain here for cotangent. This is your domain for tangent. Ranges are the same, all real numbers. Periods are the same, pi. Questions on cotangent? All right, that's it. There's nothing really more to do. What happens, I guess we could talk about this. What happens if I ask you to graph a different function like g of x equals 5 cotangent x? What does that do? What is the effect of that 5?
That's the amperage. Or the
Amplitude. Well, amplitude was with the sine and cosine, because sine and cosine kind of had a highest and lowest point, but with tangent you don't have a highest and lowest point, right? For tangent or cotangent. I heard something. It just stretches it out. All this does is scales the entire function by 5. So like think about this number right here. Remember when we plugged in pi over 4 and we got 1?
Yeah.
What would it be instead? It'd be 5.
Okay.
So it takes this point and it stretches it out by a factor of 5. It's not that we're moving every point up by 5. It's that we're stretching everything by a factor of 5. So the graph of that blue one would still go through this point 0, pi over 2. It'd still go through there, but it would just take off faster. It would still have that asymptote, but it would just take off faster like that. Do you see that? So if you were ever asked to graph 5 cotangent x, it wouldn't look a whole lot different than cotangent x would. You know what I'm saying? Like if I ask you to graph sine x versus 5 sine x, those graphs are going to look obviously different. Yes?
As you add stuff to the equation, are the asymptotes going to change?
Yes, that's exactly what I was going to do right now. Yep. I just wanted to, before we do anything, point out that changing the number in here doesn't have as much of a visual effect on the function than it does with something like sine and cosine. All right, so let's try that. Let's try and graph something like a cotangent where we throw some stuff inside and see how it impacts where those dotted lines are. We'll do it a cotangent since we've only graphed one of them. All right. Let's sketch f of x equals cotangent of 3x. Yeah, let's just go 3x. Do you remember what putting a number out in front of the sine and cosine function did? What was the impact of that number out front on the sine and cosine? What did it change? The period. Right? I gave you this formula. It was 2 pi over omega. Remember that? That was your period. This is for sine and cosine. For sine and cosine, so the period is 2 pi divided by omega. Here, that 3 in front is going to have an impact on the period. So when we were graphing sine and cosine, what was the standard approach for sine and cosine for graphing? First thing, set it equal to 0 and 2 pi, right? And why did we like 0 and 2 pi? Those are the starting and ending points, right? So I'm going to do the same thing here. But what do you think I'm going to set it equal to? What are the starting and ending points, the standard starting and ending points for the cotangent?
2 pi, pi over 2, and, well, it's 1, right?
Tell me where that entire picture lies.
Inside the period.
Inside those dotted lines, right?
So cotangent was negative pi over 2.
That was tangent.
That's tangent.
0 to pi,
0, 0.
right? The one we just graphed, we said the first vertical dotted line was at 0 and the second one was at pi, right? For cotangent, we are going to always just set this inside equal to 0 and pi. So I take the argument, set it to 0, and the argument, and set it to pi. I'll summarize this at the very end. When we finish today, which is going to be phase shift, after we do some phase shifting, we'll just kind of summarize all the functions and like how things impact it and what you set equal to what, and then we'll have kind of a general attack. All right, x is 0, and x is pi over 3. Okay, so here, what we're going to do is go to our number line, our graph. I'm going to go to 0 and pi over 3. And what am I going to put at 0 and pi over 3? What was going on at 0 and pi on our cotangent function? Asymptotes. So you need to put asymptotes at 0 and pi over 3. I've had questions before, like students ask me, how do you draw a dotted line on top of a solid line? So one of the techniques you can do is do like little diagonal dashes if you're having a hard time seeing a dotted line on top of a solid line. And then over here, so there are my two verticals, okay? Now I know that this should look like a decreasing function so long as I don't have a negative out here. What would happen if I put a negative out here? It would flip it, right? Because that's the standard thing from college algebra. If you put negatives, it flips functions over the x-axis. So, but it's positive, so this should still be decreasing. And it should cut through the middle, exactly the middle. And what's halfway? Pi over 6. So I just draw this like this. And that's it. There's nothing else for us to do here. We're really not concerned about how high or low these points are. You know, for sine and cosine, we were really concerned about this height because that was our amplitude. That was, that was going to have an impact on our range. Here with cotangent, it's taken off to infinity and negative infinity. If I draw it like that, but you draw it like this, as long as we both have the same asymptotes and the same x-intercept, it's okay. All right? All right, let's do another one. What was I going to do? I'm going to take the argument and set it equal to 0 and pi. Argument. What's the solution to the first one? 0. And the second one? Multiply 4 on both sides, divide pi, so x is 4. So I'm going to draw, let's see, 0 and 4. And at 0 and 4, I'm going to draw what? Two asymptotes, vertical dotted lines. So here's at 0, here's at 4. What comes next? X-intercept in the middle, right at 2. Is it what? That's if we had subtracted 1/2, right? This is multiplication.
You said it equal to pi, what do you mean you said it equal to 2 pi or just pi?
Pi. For cotangent,
Okay, for
it's 0 and pi. What is it for tangent?
2 pi.
Negative pi over 2 and pi over 2. Like I said, we'll do a summary of all this at the end, okay? We'll make sure we all understand. For sine, cosine, secant, cosecant, it's always 0 and 2 pi. For tangent, it's negative pi over 2 and pi over 2. And for cotangent, it's 0 and pi. Now, what am I going to draw? Is this going to be a decreasing function? No, not this time. Because of the negative out here, it's going to flip it. So it's now going to be an increasing function. Also, I have a 1/2 here. What does a 1/2 do? It kind of smashes it down. But we don't care too much about that. All right? That's what I'm telling you. We don't need to care too much about that. So like, if I flip it, it would go like this. It would go like this instead. Okay?
So it goes like a tan function then?
Now it looks like a tangent. Yep. The difference is that the period, like where it starts and ends, is different than tangent. So the 1/2 would basically bring every point down by half of what it is, but it would still look the same, wouldn't it? It would just be kind of shrunk a little bit. Let's not worry about that detail.
So we don't mark the y-coordinates on cotangent and tangent?
We don't mark the
Like in
y.
sine cos, we used to mark and secant and cosecant, you mark the y-coordinates?
That's right. We don't because the range is infinite. So there's really nothing for us to mark out. All right. That's it. That's cotangent. Let's do another one of those problems that, before we move to the next section, where you can see one of these trig functions coming into play. Let's say that you have the ground, okay? Let's say that you have this little radar station. It's a little radar station on the ground. That's a radar station.
Mind the side question.
Please do not be intimidated by my artistic abilities. It's taken years and years to refine, so if you can't draw a radar station to that detail, don't worry about it, okay? There's a radar station on the ground. Then you have an airplane coming overhead. And again, when you see this airplane, do not panic and be like, I can't draw an airplane as good as that. All right, there's my airplane. Anybody know what that is?
It Inertial jet thrust?
You can't tell what plane that is? No?
It looks like a Saturn V, maybe?
That's some plane, all right? And let's say that it is flying horizontal to the ground. And as it's flying at a constant altitude of, let's say, 6,000 feet. Is our distance. And as it flies in this direction, okay, so it is flying in that direction, this radar station is tracking it, all right? And if we connect the plane as a point down to the radar station as a point, then there's always some distance between them, right? As the plane flies over, that distance gets smaller until it's right overhead and it gets to the smallest distance it can be, which is straight up 6,000 feet. And then as it goes, it starts growing again, right? All right. Now there is also an angle. We could call this right here theta. That's the angle between the ground and the plane, which we call the angle of elevation. Let's call this distance. In a calculus class, what we would be asked is, at the moment the plane is, let's say, 8,000 feet away from us, how fast is the angle of elevation changing? Oh, I need to give you the speed of the plane, sorry. Let's just make it up, 480 miles per hour. Wait, I'm in feet here, so let me go feet up here. So let's go, I'm going to go like 2,300 feet per second. That's really fast. That's fast. Let's go 230 feet per second, which is not very fast, but it's about a football field a second. Okay, so you got this plane flying overhead, 6,000 feet high. It's traveling 230 feet per second. And I would ask a question we would ask a question, at the exact moment that it's 8,000 feet away from us, how fast is this angle changing? Now the question is not asking, when it's 8,000 feet, what is the angle? That's not what it's asking. That's a pre-calculus problem. In calculus we say, when it's 8,000 feet away, how fast is that changing? Understand the difference between those two questions? And the way you can think about it is if, let's say this plane is going really fast, really fast, really low. So imagine a plane flying overhead and you're looking at it, right? And you're keeping your eyes on it. When it's really far away, you just barely see it out there, right? You're watching it get closer and closer and closer. And as it gets closer and closer, then you have to speed up your head to watch it go by. It's like that, right? And then you watch it and it's slower. So that the rate at which you're turning your head is initially slow, then it gets really fast, and then it slows down again. Do you all see that? Do you understand that? So in calculus, we want to know at a specific instant, how fast is that changing? Well, to do that problem, we first have to find a relationship between the distance and the angle. So can you give me a relationship between the distance and the angle? Any relationship you can think of. And since this is pre-cal, you may as well think of a trig function. Sine, what does it say? Sine of theta is equal to 6,000 over d. So if I asked you to give me the equation for d, right? Find me an equation for the distance, then you could multiply both sides by d, and then you could divide both sides by sine. And that's the same as 6,000 cosecant theta. Isn't it? Because sine on the bottom is the same as cosecant. Now if I asked you to graph that, could you? Could you graph cosecant theta? 6,000 cosecant theta? Of course you could, right? How would you graph 6,000 cosecant theta? What would you graph first? 6,000 sine theta. Now 6,000 sine theta would look like this. Here's 2 pi. Here's pi. And then how high would it be? 6,000. And then negative 6,000 here, right? That's the graph of sine. That's not what we want. We want cosecant. So what would I do from here?
Move the point of origin to 6,000. From where it starts.
Yeah, yes.
And it'll dip in between the
It'll dip, yes.
4 pi. I'm trying to break it down to 2 pi. It should go through the x-axis and then come back up.
Go through the x-axis?
Pi over two.
0 to pi, we take a curve
Over
from
two.
top from the 6,000 point.
Because if it's 6,
From here?
right
Yeah,
there.
it goes there.
And it goes like a U? Okay, so remember, you do your verticals,
It does not.
right? You do your verticals like this. I'm graphing cosecant over there. And then at this top point, it goes up like that. And the bottom point, it goes down like that, right? The red graph that you see is the graph of the distance from the radar station to the airplane as a function of theta. Meaning, if somebody gives me the angle, this will spit out how far away the plane is. Okay? Can somebody tell me just visually what our restriction on theta is in this word problem?
Can't be less than 6,000.
No, theta.
And be less than 0.
What's the smallest theta could be? Could it actually be 0 though?
No, because the planes
It
at
has to be
6,000
some-
feet
some
from the
height.
ground are constant.
Yeah, I mean the only way theta can be 0 is if the plane is on the ground, right?
The Earth is curved, so if
Okay, we're not going to get into that, but yes, you're right.
the line of sight.
We're assuming this flat Earth here for this problem.
Why we know.
But we would say 0 is definitely a lower bound, right? And what's the biggest the angle could be? 180, right? Now take a look at our graph between 0 and pi, which is 180. And look at this curve. And I'm going to kind of zoom in on it right here. If we zoom in on that curve, here's 6,000. And like I said, I'm zooming in. Here's pi. So our cosecant function looks like this. Do y'all see how this function perfectly explains the distance between us and the radar station and the plane? What is happening at pi over 2? What's the value of the function at pi over 2? 6,000. When you're at pi over 2, you're straight up, right? That means the plane's up here, which means it's exactly 6,000. As the angle gets bigger and starts approaching pi, that means the distance is getting bigger, isn't it, between you and the plane? And that function shows that. As your angle gets bigger, you asymptotically approach infinity. And it's the same way the other direction. As the angle gets smaller towards 0, that means the plane is further away. So can you all see the value of that function now? Like how it models this situation? And then in calculus what we do is some other stuff, and then we can actually figure out, how fast it's turning, the angle at which it's turning. Okay.
Professor, what was the question?
What was the
What was the rate that theta was opening?
Oh, the original calculus question?
No, the pre-calc question, like what exactly did we find here? Like did we graph, that was a question, or define the equation?
There wasn't a pre-calc. What I started this with was I want to show you how you're presented in a problem in calculus and how it forces you to first come up with a trig function, which is the pre-cal part. There's the function. Here's the graph of it. But then in calculus, we do something else with it. But we have to work with the graphs. That's what we do in the calculus. We set up the equations and do something with them. Set up the functions.
How would you write the answer for that, for the theta increase? I'm just wondering what the notation would be.
Wait,
How would you write the notation for theta? I'm just curious about how you write it. Is it feet per second? Is the distance that it's open?
oh, good question. As long as you kept everything in terms of seconds, then it would be the rate. It would be a rate of change, so it would be like angle per second. Whether or not you do degrees per second or radians per second would be up to you. Most of the time in calculus, we leave it in radians per second. Right? Because if I say that I'm going to turn at 100, let's say 180 degrees per second, then that would be like 1, 2, 3, 4. So that was about 180 degrees in a second, right? If it was 180 degrees, or how about 720 degrees per second? Think I can pull that off? I don't think so.
2 turns in a second.
You think so? Should I? No, I'm not going. But that's what when we talk about like an angular speed, that's what it is. Now that's very useful, you know, if you're trying to shoot that plane down, to know seriously, right? What's the rate of change? If you're trying to lead that gun, you know, lead a gun on that plane, you need to know how fast that turret needs to be turning. I mean, look, I always tell my students, our desire to kill one another on this planet is motivated so much technological advancements, right? I mean, just to become more efficient at destroying one another has pushed science to, you know, really, right? And they used to just like lob things into castles, you know, just like hope to hit people, right?
Plague-ridden bodies. So they don't get the plague.
Yeah, I mean, it's just like, then they understood, wait a minute, you know, that's a parabola. We understand, right? I mean, that's what it is, right? So artillery, same thing, it's parabolas. If you know the function, right? If I know a parabola, if I know the actual function of a parabola, if I know that thing's function, then I don't actually even need to know anything else. I can predict where it's going to land because I know that is an x-intercept, and I can always take that function and solve it for x, and I can predict where I can put it where I want to put it. Does that make sense? So that, you know, instead of just throwing something and not caring and hoping we hit, as we started to understand and put mathematical structure to things, we became better at it. It's true. All right. I'm going to stay on task today. Let's move into phase shift, which is 7/8. Speaking of plague, you okay over there?
I'm all right. It's just that science.
All right. All a phase shift is a left or right shift of one of these trig functions. And this is it. As far as graphing, this is the last section. So we're going to put it all together in this final section. Like this is the final view of what you could see when it comes to graphing. So on a test, these are the types of things you're going to see. Like I'm not going to ask you to just graph sine. I'm going to make it a little more robust. So let's first look at the general form. Okay, that's the general form we're going to use for sine and for cosine. We'll use the same thing. So these are two different separate formulas, one with sine, one with cosine. And now I'm using the variables that your book uses. I'm not really a big fan of these, but they use omega and they use this. Do y'all know what that is? It's another Greek letter. Phi. It's actually written more like this, but I always write it like that. I don't know why. It's easier, exactly. But it really kind of looks like this, which could also be the empty set. So I don't like it, but okay. All I'm talking about right now are sine and cosine. That's it. What is A in this problem?
Amplitude.
Amplitude. So that affects this part, right? This stretch of it. Same with here. That affects your amplitude. All right, what about omega? What is the omega effect? The period, right? The period. How about the B? capital B, what does that affect?
dy left.
The up and down shift. So it's like you just take the whole picture and just move it up or you move it down, right? This omega, not omega, this, I've heard phi and I've heard phi, all right? I've heard it pronounced both ways, all right? I have a tendency to switch back and forth. So what do y'all like, phi or phi? 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 Okay, it doesn't matter. Phi, phi, pho, fung? Phi. All right, let's go with phi. So what does the phi do?
Left and right transformation.
It's a left and right shift. And you know what? Hold on. They used the minus. Sorry. Minus, minus. That's going to be a left and right shift. And that's what we were saying here. We call left and right shift phase shifts. All it does is moves a little bit where it starts and stops. All right, so for both of these, let's try and list out some things that we already know. Amplitude would be the absolute value of A. Whatever this number is in front, like if it's -3, that means the amplitude is 3. How about the period? Remember the formula for calculating the period? 2 pi over, in this case, omega, right? And we have a new one now, and that's the phase shift. The phase shift is going to be omega, I keep saying omega, phi over omega. If negative, it's actually to the left. If positive, right. Now, that's why I had to change that minus sign in the formula. Look, if I take omega, omega is this number without the negative. If I take that number and divide, phi. If I take phi and I divide it by omega, right? Take that ratio. If it's a negative number, right? If it's a negative number, then I'm going to do negative, negative, which is going to be positive. But what happens, do you remember when you add a number in a function, inside a function, it moves it to the left. And then if this turns out to be positive, then I'm subtracting it. So when you subtract something in a function, it moves it to the right. It's opposite of what you think. Do you remember that from college algebra? It was transformations. The number on the outside does exactly what you think. If you add it, it goes up. If you subtract it, it goes down. But when it's inside the function, inside the argument, it's opposite of what you think. All right. Now, I've got great news for you. There's really nothing new here, okay? There's absolutely nothing new. Because of the way that I introduced this to you, setting it equal to 0 and 2 pi for sine and cosine, there's absolutely nothing that we have to do that's new. All right? So I'm just going to give you some more problems. And these will have phase shifts in them, and we'll see them. I'd say the only thing that's going to become a little more complicated now is identifying those nice points that we need to draw our picture. That's the only thing. And maybe when we plug in, it's a little bit nastier, but really, it's nothing real new. So let's sketch this. F of x equals 5 sine of 2x minus pi. It's a sine curve. Since it's a sine curve, I'm going to set the argument equal to 0, the argument equal to 2 pi. From that, I'm going to put points, cut it into 4 equal pieces, identify my x-intercepts, test a point, and draw it, right? That's what we're going to do. So my argument is what? 2x minus pi, right? That's the argument, the whole thing. Set that equal to 0. Take 2x minus pi, set it equal to 2 pi. What is the solution to the first equation? 5 or 2. Solution to the second equation? 3 pi over 2. So we're adding pi to both sides and then dividing by 2. On a number line, I'm going to put negative pi over 2 and 3 pi over 2. And watch how I do this. Notice I'm not really paying much of attention to anything else other than the fact that these are both positive numbers and that this one is bigger than this one. So I'm going to put it to the right of it. And then I'm just going to cut that in half. So I've got to find the midway point. To find the midway point, we add these up and divide by 2. So let's add them up. What's pi over 2 plus 3 pi over 2, all of that over 2. So what is it? 4 pi over 2 over 2, that's going to be just pi. So halfway is pi. Maybe you could just look at that and see that, all right? But I'm just showing you the mechanical part of it. If it's not obvious, this is pi. And then you have to find halfway here. So how do you find halfway here? Add these two, divide by 2. So take pi over 2 plus pi, and then divide the whole thing by 2. To do the numerator, I've got to get a common denominator, right? To add these two, common denominator here. That's 3 pi over 2, which is 3 pi over 4. And then halfway here, you do pi plus 3 pi over 2, add those together, and then divide by 2. What would you get?
5 pi over 4.
You should get 5 pi over 4. Does anyone feel like they're going to have trouble getting these? Or want any more clarification on how to get those? This one, you want me to do this one? Okay, so on this next one, I'm very happy. Today I've had 3 people ask questions. This is good. This is a good day. Okay, so I'm taking pi plus 3 pi over 2, and I'm going to divide it by 2. I have to get a common denominator here. So this numerator is going to be what? 5 pi over 2, but then divide that by 2 again, you get 5 pi over 4. Is that enough or detail there? Is that okay? Yes? Okay. So 5 pi over 4. All right, what are we trying to graph again? A sine. So sine is the one that has the 3 points, right? It's like each of the endpoints in the middle point are x-intercepts. And also I noticed that there's no up and down shift here, right? I'm not going to move this thing up or down. So these x-intercepts are going to stay here. Here, here, and here. And then what comes next? Very important.
Test point.
Test point. You've got to test one of these points. And you don't want to test the x-intercepts because they don't tell you anything other than, if you plug those in, you're going to get 0. So why don't we take this one and plug it in? I'm going to test that one into the original function and see what I get.
Professor,
Yes.
if you have a positive amplitude, is it still necessary to test the point?
Yes. I highly recommend it. I'll show you an example of something dangerous after this. Okay. Plugging that in, 5 sine of 2 times 3 pi over 4 minus pi, right? That's all I'm doing. Now what's 2 times 3 pi over 4? 6 pi over 4, which is 3 pi over 2. Okay, so these together is 3 pi over 2, so I have 5 sine of 3 pi over 2 minus pi. Put those together, right? 3 pi over 2 minus pi, you get a common denominator and subtract. You just get pi over 2. Common denominator, 2, 2 on top, bottom. Subtract this. What's sine of pi over 2? Sine of pi over 2? 1 times 5? 5. So we're getting 5 out here. At 3 pi over 4, it's spitting out 5. So that's up here. And that's all I need to draw the picture. Because I know that the first arc of the sine right here is going to go up like this. Then it has to come down, and then it has to do the opposite in the next region. So there it is. That was supposed to be negative 5 down here. I don't know if it looks like it, but close enough? A lot of instructors and a lot of textbooks like you to graph 2 periods of these trig functions, just to make sure you understand what you're doing. I'm not going to ask for 2 periods, but can I just show you real quick how we would do 2 periods? All we would need to do to do another period is extend this picture out, right? And make it about the same length, cut it into 4 pieces, and then you just need to figure out what these are. So you know it's still going to do this, right? But where are these? So can you tell me from this what the period is of this? What's the period of this? It's just pi, and you're getting that by taking omega, which is 2, and dividing omega into 2 pi, and that just gives you pi. So that means for me to figure out this point right here, I need to take this right here and add pi to it, right? Take that, add pi. So if you did that, if you added pi, what would you get?
5 pi over 2.
5 pi over 2, because you'd have to get a common denominator. So this would become 5 pi over 2, and then you could play the same game, cut that in half, cut those in half, and then you'd have more points, right? That's how you would do that. All right, so there was a question about whether or not you always have to, since we know that this was 5, can we just like graph it up and not worry about it? And it's possible that you could run into some danger. So I'm going to try and change the problem just ever so slightly to see if I can make it mess up. Okay, let's try that one. The only difference I did was I put a negative in front of the 2x. You all see that? How does that change things? Does it change our x-intercepts? You set this equal to 0. And you should get x is negative pi over 2. You're going to get negative pi over 2 this time, right? And then when you set negative 2x minus pi equal to 2 pi, which is the next standard step, you add pi to both sides, which gives you 3 pi. And then divide by negative 2, and you get x is negative 3 pi over 2. So far, is that all right? Now you graph this. Those are both negative numbers, aren't they? Okay, so here's negative pi over 2. Here's negative 3 pi over 2. Aren't those the same numbers we just had, but negative? Okay, so if that's true, then what was our midway point on the other one? It was pi, so it's going to be negative pi here. What was this one and this one then?
Negative pi over
Negative
3 pi over 4.
3 pi over 4, and this one will be negative 5 pi over 4. Do you see how you could get those? Just add them together and divide by 2 again. Okay, and we also know that we have x-intercepts here, here, and here. So if you follow the logic that, I guess this is, I'm just kind of trying to challenge your question back, like, how are you going to draw this? If you did not test a point, how would you do this now? Like, where is it going to, which way is it going to go?
I mean, will it still go the same sine function as it had for the positive one?
Okay, so yeah, that's what I'm saying though. Do you want me to draw this?
No, that's it.
You want this side?
Yeah.
Why that way?
Because that's how the normal sine function goes.
No, I thought the normal sine function went like this.
Oh, so it goes from down and then.
No, I'm asking you, this is why I'm saying it's dangerous, because how would you do this? Would you still want to draw it like this, or would you want to draw it like this?
I would draw it from down to up.
You would go like this,
Yeah.
so that it would look like this.
Yeah.
Okay, let's just see what it is. All right, let's see what it is. So why don't I test a point? How about this one? What is 5 sine of negative 2 times negative 3 pi over 4? And then what, minus pi? Is that what I'm doing? Okay, so what do I get here? 6 pi over 4, right? Okay, 6 pi over 4 is the same as 3 pi over 2. 3 pi over 2 minus pi is pi over 2.
Negative.
No, this was positive, right? Yes? Let me do it. It is negative, but hold on. This was 3 pi over 2 minus pi. Hold on. What is
Yeah, pi over 2.
pi over 2? Y'all okay with this? What's the value?
5.
5, which means that it's up here, which means when I draw it, it has to look like this, which is not necessarily what you might have been thinking, right? That's why I say it's dangerous. Testing a point will make sure you don't have that confusion. It's not that you're... Do you remember me telling y'all I'm trying to give y'all like a technique that would give you the shortest way to get there and cut out any of like the fluff stuff that we need? And that if there were a shorter way, I would tell you. So like if it would always turn out that it would be left side up, right side down, if this was a positive number, then I would just tell you that. But because this could happen, it's best that we test a point. Everyone okay with that? I guess one way you could look at it is if you're like standing here at the origin looking out, then with the 5 on the outside, you see the sign go up first and then down. And then if you turn around and look this way, you are still seeing the sign go up and then down, right? It's like kind of a reflection over. And that's what negatives in front did. If you remember that from college algebra, if you put a negative in front of the variable, it was a reflection over the y-axis. That's kind of what happened there. So always test a point to be sure. That was a good problem, good question. Let's move on. How about negative 4 cosine of 5x plus 3 pi? Shoot, I forgot to ask y'all something on the last 2 problems. I apologize, but I forgot. The phase shift. I mean, this whole section's about phase shift, and I forgot to ask you. I mean, we're drawing these, right? But we never answer the question. So before we graph that, just real quick, the phase shifts. I'll write the function out the way we had it. It was 5 sine of 2x minus 3? Minus pi. Okay. That was the first one, right? And then we changed it to negative. But on this one, what would be the phase shift? So we take the phi, which is this, but ignore the negative. So it's pi over omega. Omega is 2. So this is pi over 2. Now, is that a shift to the left or to the right?
Left or right?
Positive. If this is positive, it's going to go right. So remember when we graphed this, it looked like this? Started out at pi over 2, didn't it? And it did that. Isn't that just the sine function moved to the right by pi over 2?